electrolysis. Electrolysis is just the opposite of voltaic cell. In a voltaic cell, you have a battery. Batteries will do work for you. In electrolysis, you actually need to put in energy to get that process going. Okay, so it's basically an energy sink. And the reason why it's an energy sink is because whenever you're trying to drive a reaction in the opposite direction, you're going to need energy input. That's the difference between a voltaic cell and an electrolytic. We call this electrolytic cell. So let's take a look at this and look at the difference between the two. Okay, let's take a look at the difference between the two. This right here is a voltaic cell. Again, oxidation still occurs at the anode, reduction still occurs at the cathode. Oxidation at the anode is where your electron source is. You generate electrons there, lose electrons, oxidation. And then it drives it to the cathode where you gain electrons, reduction. And the process of moving those electrons through an external wire, you can measure the voltage or you can do work. That's just opposite from a electrolytic cell. In electrolytic cell, this right here is your electron pump. You need to pull the electrons from one side and push it to the other side. Okay, it's an electron pump. And what is an electron pump? It's nothing more than a battery or a power source. So what we have is we're drawing electrons here and we're pushing electrons here. So you're drawing electrons. That means that according to a battery's orientation, to track electron, this side has got to be the positive side of the battery. Okay, the positive side of the battery will attract the electrons because electrons are negatively charged. And then the negative side of the battery will repel electrons because the same charge will repel each other and then push it down here. So that's why we call this an electron pump, because it's pulling electrons from one side and pushing it out the other. Now, since this is where the electrons occurs, that part is still the anode. That's going to be oxidation. Okay, oxidation is always where the anode occurs. Anode, because that's your electron source. This side is going to be your cathode, because that's where the electrons are heading, and so you're going to be reducing. So anode is still oxidation, cathode is still reduction. The only difference, there's two major differences, okay? One is that the signs are opposite, whereas in a voltaic cell, this side is negative. In a electrolytic cell, that side is positive. Why is it positive? Because that's connected to the positive side of the battery. Okay, the positive side of the battery. Even though the battery is in this area right here, that wire extends all the way down the solution, and so that's positive all the way. The positive, of course, is going to be attracting the electrons. Going to be attracting the electrons, and then the electron's going to go through and then get repelled out. So the signs are opposite between an electrolytic cell and a voltaic cell. Whereas in a voltaic cell, it's negative at the anode. Electrolytic cell, it's positive at the anode. And then the other difference is the color. Whereas this would be black and this would be red, this now is red and this is black. Okay, and then the third, okay, there's three major differences. The third and most probably important is that voltaic cells are spontaneous. It's going to happen. You get a positive electrochemical potential. Electrolytic cells are not spontaneous. You need an external source. So you're going to drive a negative potential with an external source, basically your battery. That's the major difference right here. Okay. So when it's spontaneous, delta G is negative. When it's not spontaneous, delta G is positive. So that's the major source. So let's take a look at an electrolysis process. This is an electrolysis process. And let's say we're trying to, say we have a salt. This is basically, again, the diagram of the battery. It's going to be positive orientation at the anode, negative orientation at the cathode. It's going to be attracting the electron. And we have this right here, two electrodes. external potential power, source of energy. You've got drive by non-spontaneous reaction. Okay, those are the major features of a electrolytic cell. Let's take a look at electrolysis. What happens when we do electrolysis? Okay, and you may not be, electrolysis might be an intimidating word, but you guys know about electrolysis because the way they electroplate utensil so that it's silverware, that's electrolysis. The way they nickel plate fixtures, that's through electrolysis. So let's take a look at this right here. This is an electrolysis process. And what we're trying to do here is we're trying to figure out what is the reaction that is going to be driven. So what we have here is sodium chloride. This is molten salt. And the question is, can we drive this reaction? And if we drive this reaction, what is the potential that is required? In order to do any type of electrolysis process, you need to figure out what chemical, what species are in your is in your setup. So in this particular case, we have electrodes. Platinum inert electrodes, not going to do any chemistry, but we have sodium chloride. Okay, you got to know that sodium chloride is made out of sodium ions and chloride ions. Okay, and that's what's going to do the chemistry for you. The sodium, well, they can only go in one direction. They can only be reduced. Sodium plus to sodium 0. So that's a reduction. You can never go from sodium plus to sodium plus 2. That's not going to work. Chlorides, they only go from chloride minus to chlorine gas, Cl20. It never goes from Cl minus to Cl minus 2. You guys have never seen a Cl minus 2. Okay, so you know the tendency of what these ions are going to do. At the anode, again, it's going to be oxidation. What's going to get oxidized? The chlorine is going to get oxidized from Cl minus to Cl2. It goes from -1 to 0. What's going to get reduced? The sodium is going to get reduced. It goes from sodium plus to sodium 0. What are those potentials? Sodium, if you look at the standard reduction potential, is -2.71. That's the oxidation. That's the reduction potential. If you look at the oxidation potential for the chlorine, that's -1.36. So the question is, what is the energy required to drive this reaction? Well, there's an oxidation, there's a reduction. So all you've got to do is add these two potential, and you're going to need a battery with 4.07 minimum, if everything was correct, to drive this electrolysis process. That's the amount of energy in order to generate chlorine gas on one end and sodium metal on the other. You actually need more because of something called overpotential. So that part looks pretty easy. Let me show you another. Okay, let's look at water electrolysis. In water electrolysis, again, we have an inert electrode because water can't be used as an electrode. And the ions that are involved, or the chemicals that are involved, is H2O. And water can undergo both oxidation and reduction. That's what you see here. When we look at the reduction of water, reduction is gaining negative charge, okay? So if we take a look at the hydrogen ions, H plus going to H2, plus going to 0 is a reduction. The charge is going down. So that's the reaction that we see right here. Water, hydrogen in water is plus, but in H2, it's 0. So that's the reduction process. Hydrogen here is plus, oxygen here is -2. So that's not the species that's undergoing oxidation reduction. How about oxidation? Well, oxidation, just by the very word, means oxygen's involved. So water here is, oxygen here is -2, but oxygen here is 0. So it's going from -2 to 0. That's the oxidation process. Anyway, I just wanted to show you that so that you know that which is the oxidation, which is the reduction reaction. Just find these reactions somewhere and know what their potentials are, because the potential for the reduction of water is -0.83 the oxidation of water is minus 1.23. So in order to electrolyze water, so you get hydrogen and oxygen, you're going to need a minimum of 2.06 volts. Okay, so the question is, if we can do this to water with 2.06 volts, then why can't we just make hydrogen directly and run our hydrogen economy? Because that's what people are leaning to, is using hydrogen like fuel cells in order to drive our cars. The problem is that if you use a battery with 2.06 minimum energy, that's more energy than the hydrogen that you get out. When you take hydrogen and you burn it as a fuel, you get less energy than 2.06. So it's not cost effective. Okay, it's not cost effective. But again, if you want to do electrolysis on water, theoretically, you need a minimum of 2.06 volts to drive that reaction. Let's take a look at one more. Let's say we have salt water. We have salt water. What is the process that's going to go on? Again, you always need to break it down to what chemicals you have. We have platinum wire, we have sodium chloride, and we have water. What are the species that's going to do chemistry? We've got sodium chloride and water. Platinum's not going to do anything. It's an inert electrode. So what are the chemicals that are going to undergo reduction? Cathode is where reduction occurs. We already said that sodium's going to undergo reduction. Sodium plus the sodium zero, and water can undergo reduction. So there's two reactions that can undergo reduction, and there's two reactions that can undergo oxidation. And here they are. That's my oxidation, and that's my reduction. Which one wins out? The one with the most positive potential, or the least negative, So let's take a look at that potential. These two are going to compete between each other at the cathode. One's at negative 2.71, the other one's 0.83, which is the winner, 0.83, because that's the least negative. These two are going to compete at the anode. One is going to be minus 0.36, the other one's minus 1.23 volts. Which one's the winner? The one that is the least negative, negative 1.23 volts. So in the end, if you've got salt water and you want to make chlorine from that, I hear that the chlorine is low in abundance. I hear that chlorine is low in abundance these days. And the reason why chlorine is low in abundance is over the COVID shelter in place, everyone was using their swimming pool. So the chlorine is, you can generate chlorine this way if you can do electrolysis, but not, because what you would do if you were trying to do this with salt water is you would actually get the oxidation reduction reaction of water, because that's the path of least resistance, Okay, the one that is going to be the least negative or most positive is always going to be the path that's going to be driven. That's why you have to do the calculation. Take a look at these next few reactions right here. This is the same one that I just gave you. Okay, let's take a look at this one right here, magnesium chloride. I'm not going to talk to you much about this because I want to get to the last point in this discussion. If you've got magnesium chloride instead of sodium chloride, again, look at the chemical species that are involved. Look at the reactions that are undergoing oxidation, which are the reactions that are undergoing reduction. If you've got magnesium plus 2, that's only going to do reduction. Look up their potential and figure out the competition between these two. Which one is going to be favorable? It's going to be that. The competition between these two, which one's going to be favorable? It's going to be that. So if you got magnesium chloride ions in water, you're not going to get oxidation reduction with magnesium chloride. What you end up with is still the electrolysis of water, just based on the electrochemical potential. I'll give you one more example in which I keep going back to this one. Okay. So here is a reaction in which water is not the dominant reaction. This particular reaction, we have this right here, nickel bromide in water. Nickel has a potential minus 0.28 volts. Bromine has a potential minus 1.05 volts. And then we have the water. You always have to keep the water reaction if you're doing it in aqueous medium. These two are going to compete, which is the winner, minus 0.28. These two are going to compete, which is the winner, minus 1.065. So what is the reaction that's going to occur? It's actually going to be the oxidation of nickel and the reduction. It's the oxidation of bromine and the reduction of nickel. Why? Because that's the path of least resistance. That's the path that is going to be the least negative. And so when we do this, when we do this, actually, I don't have that, but you should, that would be the reaction. I wanted you guys to do this in class, but we're not going to be able to do that. That would be the reaction right here. Why? Because it's a path of least resistance. I want to get to this point right here, this process right here. Okay, take a look at this problem. Solve it using dimensional analysis. This is an electrolysis process. And tell me what electrode, what mass of silver is going to be plating out at the electrode. Okay, this is best done using dimensional analysis. What you want to do is remember that you have 72 minutes. That's a part of the given. What you've got, Faraday, 96,485 coulombs per mole of electrons. And you should be able to figure out the E0 for this. And if you do that correctly, this is volts, this is joules per coulomb. Okay, if you do this correctly, then you can come up with the moles of electrons. And then the moles of electrons is related to the moles of silver, which will give you the mass of silver. So that'll be your homework, okay, for next time. And then we'll talk about this short at the beginning of next time, and then we'll go to coordination chemistry. This is an important problem because this is a problem that you usually see in the MCAT, okay? And that's why I wanted to get to this type of problem. You don't have to know any special chemistry for this problem, just know dimensional analysis and how to go from minutes to mass of silver. And how do you go from minutes? You can go from minutes because an ampere is coulombs per second. And what it says is that you have 6.8 amperes during this electrolysis. So let dimensional analysis work for you in this problem. And you'll see again the magic of dimensional analysis. And then we'll talk about this next time. Sorry about rushing through the last bit. I just wanted you guys to be exposed to electrolysis so you can see that those problems require you to think about chemistry. What are the natural process for a cation? It's a reduction. What is the natural process for an anion? It's an oxidation. You need to use the electrochemical potential to figure out what is the reaction that will win out at the cathode and the anode in electrolysis. This is a problem where you're doing electrolysis, and of course electrolysis is going to be non-spontaneous reaction. So what you need to do is you need to make sure that you have a power source to drive that reaction, okay? And thing you want to always do in these types of problem is break it down to what you know. And what you know is an ampere equals a coulomb per second. A Faraday is 96,485 coulombs per mole of electrons. Okay, those are the two things that you should know in terms of fundamental constants. Okay, And then the problem says you're going to be electroplating silver. So that means that you're going to have metallic silver. Okay, so probably you're going to have silver in solution. That could be like silver nitrate. And you're basically causing the reduction of silver because it's going from silver plus to silver zero. Okay, so that's the reduction reaction. So remember, reduction is gaining electrons, reduction, and the charge is going to go down. So if you think about reduce, the charge is going from a higher positive charge or some charge to a lower charge. And that's what you see right here. Silver plus going to silver zero. And it tells you that you have about 6.8 amperes. And you're electrolyzing this particular, you're operating it for 72 minutes. Okay. And the minutes come in because you have time right there. A current is a coulomb per time. So with that, you should be able to solve this problem using dimensional analysis. You could certainly change this to seconds to be consistent with amperes, but you can also work it into your dimensional analysis. Let's start with 6.8 coulombs per second. Remember that an ampere is a coulombs per second. Okay, and then you're going to have to multiply this by time. Why? Because seconds in the bottom. So my time's right here, 72 minutes. But minutes is not the same as seconds, so you need to convert that to seconds. And you guys know that for every 1 minute, you have 60 seconds. So right away, that is going to cancel with seconds, and minutes, of course, will cancel. So all you have left is coulombs. Remember that you can remove coulombs by Faraday's constant, and Faraday's constant is related to the moles of electrons that is transferred. So you have coulombs right here. So you can put 96,485 coulombs per mole of electrons. And the reaction that you're looking at is this right here. Okay, you're looking at this reaction right here. And it basically means that for every 1 mole of electron, you have 1 mole of silver ions or silver. Okay, if it's 2 electrons exchanged, then it'll be 2 moles of electrons per mole of metal, depending on the reaction that you have. But in this case, it's 1 to 1. So let's go ahead and do that. You have 1 mole of electron per 1 mole of silver. And then you guys know that, well, you could look it up, but silver has an atomic weight of, let me just see, 107.87 grams per mole. So we can put 107.87 grams per mole. And you can see that, again, using dimensional analysis, we now have the mass of silver in grams, and that would be the answer. So I didn't know any equation, I didn't know any electricity, I just used dimensional analysis. Again, I can't emphasize, if you are in science and you're doing these types of problems, you need to understand. I'm trying to find my calculator here. Okay. Calculator. Well, I'll show it to you in the next step. So let's take a look at the results here. Okay. And I'll show you that it's basically dimensional analysis. So again, you can see 72 minutes, 60 seconds per minute. And then I'm using the 6.8, which is that right there. I'm using 96,485, that's Faraday's constant right there. Okay. Then I'm using 1 mole per 1 mole of 1 mole electrons per 1 mole of silver. And then I'm using the atomic weight of silver. And if you just do the math, you in 72 minutes, you played out 32.84 grams of silver. Okay, so again, the power of dimensional analysis. So if you see a problem like that, because I remember that in the, not that you guys are going to be taking a standardized ACS exam this semester, we've done away with that because people have students from the past would basically copy the solutions and hand it along. So we're not doing that. We're for your final, each instructor, each of your Chem 201 instructor is writing their own final. So that's what's happening for you guys as well. I'm writing my own final, and what you should do to prepare for that, because I know it's less than a month away, is take a look at my sample exam in my website for that. So this is a problem that you would have seen in the ACS standardized exam. It's a problem that was presented, and it's also something that you guys should know if you're taking the MCAT. Again, the utilization of dimensional analysis. Okay, so I'm going to stop there. You guys should review the battery chapter real quick. Just be familiar with the reactions for different batteries. In that chapter, let me just give a few words on that. It talks about batteries. And remember, batteries are nothing more than voltaic cell. You can actually create your own battery using potatoes or lemon. Okay, you just need an anode and electrode. The juice in potatoes and lemon will serve as the electrolyte. So that's basically the salt bridge. And then you take two wires coming out from like zinc and probably copper. That would work well. And then you hook it up to, say, an LED light or a voltmeter, and the electrons will transfer. So the thing about batteries, and there's a history around that, was, it was first sort of created back in the 1800s, but those chemicals were aqueous solution. What happens in aqueous solution is that the concentrations start to change over time as the reaction proceeds forward. And you know that from equilibrium. As the reaction proceeds, the reactants will go down, the product will go up. When that happens, then the amount of electrons that are going to transfer, the electromotive force, the E0, is going to get more difficult. It's going to be less efficient. And what happens is that the voltage drops. So the problem with those batteries is that over a short period of time, you couldn't use it anymore, because once the voltage dropped, then if a certain device requires, say, 1 volt, and the voltage drops below that, then it couldn't operate that particular device. So someone came up with a solid state battery. And a solid state battery, everything is in the solid state. If you take a look at equilibrium, you see that solid state is not involved in the mass action expression. If it's not involved in the mass action expression, then you don't have to worry about a voltage drop, because the concentration never change. What does happen is that once you exhaust the material, then the voltage will stay constant and then drop to 0 once you've exhausted the material. Of course, that's theoretical, okay? Theoretically, the solid state material would get exhausted, and you would go from like 1 volt, if that's your voltage for that reaction, to 0 volts. But you get complications. And so eventually, even your Duracell batteries or ever-ready batteries these days, they tend to go decline, and once they hit a threshold, then they don't work anymore. You dispose of them because of their disposable battery. But theoretically, what's supposed to happen is they should maintain a constant voltage and then drop when the solid material has been exhausted. And for the most part, that's what happens. That's why we went with the alkaline battery. Okay, we went with the alkaline battery, and because those are solid state battery. Now, the battery in your car is completely different. That's not a solid state battery. What happens is that you got lead sulfate and lead oxide and lead, actually producing a common product, lead sulfate. So what happens is that when the anode and the cathode produces a common product, that's really helpful, because when you reverse that reaction, then the common product can break back to its reactant. And that's how you can recharge your car battery all the time. Of course, what happens is that these materials played out on the electrodes. And if you hit a bump, then that material sort of cakes and then drops to the bottom. So it's not available. It's not in contact with the electrode anymore to be reversible. But if you look at your car battery, there are 6 cells. There are 6 places where you can fill it with only distilled water. Okay, that's because it's 6 cells. Each cell is about 2 volts. 2 times 6 is 12 volts. So your car battery is theoretically 12 volts. It's actually higher because the concentration of the acid is actually higher than 1 molar. So if you look at your display in your car, if it's reading you a voltage, it'll be higher than 12 volts. And in fact, it should be higher. That way you get extra juice to start your car. So if the alternator is not working, okay, that is the device that recharges your battery, then every time you use it, the reactants are going to convert to the product without regeneration of the reactant. And then your battery sort of loses power over time. But because your alternator is working, which recharges your battery, then usually that reaction is reversed as you're driving your car and the alternator is working. So that, in a nutshell, is batteries. Okay, these days they're doing a lot of research using solid state batteries, lithium batteries as well. Why lithium? Because remember what we talked about in terms of the standard reduction potential. The 2 extreme chemicals are fluorine and lithium. So if you take a look at those lecture notes, it shows you how those lithium battery works. And then I just heard a report that Toyota is actually coming up with a solid state battery that takes 10 minutes to charge. And then you can go about 300, 400 miles. So that's going to change the game for everyone if they do that. I don't know if I really believe that story until it comes out, but that's what I've been hearing. And then, of course, Elon Musk and his Tesla car, they're making the battery much more efficient. So you can see that if you want a job, go into that field. It's going to be opening up as far as how to store energy long term, because we certainly have windmills and we have solar, and that's the green revolution. But solar only works when the sun is out. Okay, we need a way to store that energy that we're harnessing from the sun, and the best way to do that is different devices. One of them, of course, is batteries. So I just want to mention that so that we sort of wrap up this particular section, and the fact that electrochemistry is very relevant in today's society.